Correct. I start
Great.
recording. I admit Tomek. Hello, welcome everybody. It is my great pleasure to introduce MARIUSZ Tobolski, who recently did his PhD summa cum laude. And he will speak about part of his PhD thesis, which concerns classical topology. It's his joint work with Ludwig and Alex Kirvasitu. And well, it's all yours. Take it away.
Thank you very much for the introduction. So, as Piotr mentioned, my talk will be about pure topology. So that might be bad news or good news, depending on your standpoint. And let me share the screen with you. So this will be a board talk. I should be able to. Okay, so can everyone see my screen?
Yep, I see your screen.
Yes.
Great.
Yes.
So the title of the talk is Borsuk-Ulam theorem for locally trivial compact G spaces. So as you can see, it's only topology, and it's, well, as I said, it depends. It's joint work with Alex Kirvasitu and Ludwig Dąbrowski, who is here virtually.
Be careful what you say.
Yeah, of course. But also he can help me out if I'm,
of course, yes,
lost or anything. So, so this is a talk about topology and about a nice result, which is a generalization of the Borsuk-Ulam theorem, but it is inspired by noncommutative geometry or noncommutative topology, and I will say few words about that. I'll start with the actual Borsuk-Ulam theorem, just so we know what I'm talking about. It might be stated in many, many ways, but one way is that for every continuous map which starts from the n-dimensional sphere to the n-dimensional Euclidean space. There exists point x in a sense such that f of x equals f of minus x.
Mary,
And this is.
Do you want the same n? You have the same n on the sphere and on Rn. I'm just asking. Do you want the same n?
Yes.
You want the same n?
The
Yes.
same n. Yep.
Okay.
And this is a classical result. It's well known. It's not that every undergraduate student will know this, but it's very well known. It has many applications, many different formulations, and so on.
and it's a result from 1933, if I remember.
Oh, yeah. Yep.
1933. Yeah.
So
I guess it's immediately true if the n on the R is equal to or less than the n on the sphere, right?
Yeah, I mean, you can embed Rn in Rn plus 1 and so on. So
Yep.
Yeah. Right. So this will be true as long as the n on the R is equal to or less than the n on the sphere, right?
I would presume so. Yeah.
No. Is that? Yep.
Because you don't shrink anything by embedding, and this is, you can easily have an equivariant embedding.
So that's 1933, proved by Borsuk and conjectured by Ulam.
Woo. Did it use algebraic topology to prove? How did it?
Oh, there are many proofs, and well, the one in the original paper, he proved 3 different formulations, and they used there's some, I think it was more geometric.
Okay.
But I'm just from the top of my, I don't know if I might be wrong with that. So
Okay, great. Okay, good.
So now there is a reformulation of this theorem, which was inspired by noncommutative geometry and the work on joins. So I'll start with the definition of a topological join, and then I will reformulate the theorem. I'll formulate the conjecture of Paul, Ludwig, and Piotr, and then I'll try to show the state of the art, what we can prove about this conjecture. But first I'll need to define the join. And if I have 2 topological, maybe one disclaimer, that all spaces are assumed Hausdorff and maps continuous.
About locally compact. You want locally compact?
Oh, I'll work mainly with compact spaces even, but there will be Rn. Just I'll use Rn at some points, so I'm not assuming. I just don't want to write down Hausdorff again and again. That's a long word.
Right.
So this is how in the French would do it in Bourbaki.
Right.
So compact will mean compact Hausdorff. So if I have 2 spaces X and Y, their join is defined as follows. So I take the product of the interval with X and Y, and I divide by a relation. And the relation is just, in words, it's at one endpoint of the interval, I'm shrinking X to a point, and at the other endpoint, at 1, I'm shrinking Y to a point. So in symbols, this would be something like that, when I have 2 different elements, X and X prime in X, and some fixed element Y. Okay. And here it's the other way around. I have some fixed X and I have Y and Y prime in Y, 2 different elements. So for any 2 elements like that, they might be the same as well, of course. So this is the join, and let me give you one example, which is important for the Borsuk-Ulam theorem, is that if you take 2-element group, and I'll denote it by Z mod 2, because if, I'll use p-adic, I'll talk about p-adic integers as well, so that's my notation for the 2-element group, and you take the join of Z2 with Z2, this is homeomorphic to the circle. And if you want to have a nice picture, if I have my interval 0, 1, and I have 2 points here, right? Because I have to shrink this everything in, let's say, X axis. And here I'll have 2 points as well. And then in between, I'll have 4 lines, right? Because it's the product of, well, maybe. Let me draw the 4 lines. And what happens? So in between there are 4 lines, and now I have to shrink first here, like this, and then I have something like this. Oops.
Mhm.
And then you can see that it's homeomorphic to a circle for sure. Nice, and that's the picture to have in mind. And then if you iterate this, you have that Sn is actually the n-fold join of Z mod 2Z. And I have n+1 copies, +1 copies, oh, sorry. +1 copies. But only n symbols of the join, right? So my notation for this will be Z mod 2 to the power, to join power n. So this is different if you work with, I don't know, tensor product of modules, this would be different. But because if I take 0 here, this means I'm talking about Z2. So by definition, this to the power 0 is Z2, because I'm counting the number of those asterisks, so whatever, the stars. Okay, so that's how you can see the sphere as an n-fold join of Z mod 2Z. And if you look at the definition of the join, so you might wonder, because I want to have some group actions, and in particular there's this antipodal action on the sphere of the two-element group. And the fact is that if I have two G spaces, so if I have some, maybe let's start from the group. So if I have a group G, so G some, let's say compact group, and X and Y are two G spaces, then there exists an action of G, called the diagonal action. By saying that it exists, I mean that it is a continuous action, because it's easy to write down the diagonal action, because if you look at the definition, right, you have just action on X, action on Y, and you know how to write down the action. It's just the diagonal action, and you act trivially on the, and you act trivially here, right? And here you have the G action, and here you also have the G action. But this action might not be continuous, and I don't want to go into the details, but if your group is compact or locally compact, or even there is a more general, if the spaces that you look at are just direct limits of compact spaces, let's say, this action will be continuous. But if you have something which is not locally compact, it might, if G is not locally compact, the action might fail to be continuous. Okay, but I'm sticking with compact groups. So I have an action.
And actually compact spaces, right?
I'm not sure. I think it might be enough that just the group is.
Yeah, but in your talk, you'll be talking.
In my talk, I'm also talking about compact spaces. Yep.
So then everything for a certain is the induced action is continuous. But what Marge was referring to is that it's really not at all so obvious that the obvious induced action on the join, that the diagonal action is continuous. That's not at all obvious.
Yeah, thank you. So we have the action, and then the diagonal action of Z2 on this space, which is the sphere, which I wrote down. So the diagonal action here.
Well, I have a question for Piotr.
Okay.
So you're making the point that the continuity of this action, there might be a problem with the continuity.
Exactly.
Do you have an example that shows that?
Well, if you go beyond locally compact, there is a paper of Whitehead, which I believe even has Borsuk-Ulam in the title, with Ludwig and Mariusz, we studied in Trieste on Blackboard for many, many hours. We went through detailed proof, and indeed, you see here the whole thing is that taking the product topology and taking the quotient topology, these two operations do not commute without assumptions. And if I remember correctly, a sufficient assumption is that at least something is locally compact Hausdorff. Without it, you can go wrong. So take like rational numbers. Q with this is not locally compact Hausdorff space, and then you can get I cannot give you an explicit counterexample, but it wouldn't be anything very bizarre. It would be something like the space of rational numbers with its natural topology, which is not locally compact Hausdorff.
But what's the group? Oh, you mean that will be the group?
Well, I don't remember. I don't remember the exact setup. I just remember the source of the trouble, and
okay.
Yeah, could be group, could be probably the rational numbers as well. Yes.
Okay.
Yes.
And
yes, I think you could take the join of Q with Q and act diagonal action by Q, and it might fail to be continuous. I think so. Mariusz, what do you think?
Yeah, that will probably not work, but also it's not the question of group action. It's just question of what Piotr said. This question of product topology and quotient topology. So if you take first the product and then the quotient, and what happens is that the group action is just a map from the product, right?
Right,
so,
right.
So that's the Whitehead lemma is just talking about these kind of nuances that you get when. But I also, because with Piotr we worked out this lemma and we never bothered to find any counterexamples. That's a good question.
Yeah, yeah.
Okay, so let me continue. I just want to stress that this action, if you take the diagonal action on the n-fold join of Z mod 2, so, which is homeomorphic to Sn, as I said earlier, this is as Z2 spaces, these two spaces will coincide, so they'll be isomorphic. This is the antibodal action, right? That's why. So now I can reformulate the Borsuk-Ulam theorem. So I'll use the abbreviation. So the
Mariusz, before I forget, you can save everything you write, yes?
Yes.
So because it's important, normally I ask people to send me slides, but for you it will be whatever you save from your handwriting, okay?
Okay. So so the reformulation goes as follows. We say that there's no single 2 map from Sn join or Sn minus 1. Let me 2 Sn.
Mm-hmm.
And this is this you can show that this is equivalent to the original Borsuk-Ulam theorem, and it's not that hard. So just some, you need to do some logic and some negations and some contrapositives and so on. You arrive at this, and you need to know what the action is here. So here you have the diagonal action, the diagonal Z mod 2 action, and here you take the antibodal action, right? So that's the reformulation, and this you can immediately think of some generalization, and that's actually what. So I'll write down the conjecture. Oh. By Paul, Ludwig, and Piotr. They're all in the audience, so that's a
yes, we are.
Thing to talk about someone's conjecture, and you have all 3 people.
Conjectures.
The conjectures, yeah. So the conjecture goes as follows. So it just generalizes this. You take, instead of any compact house of space, instead of Z mod 2Z, any non-trivial compact group. So G is a non-trivial compact group. And X is maybe not any compact house of space, because there's this action, the antibodal action can be, it's easy to see that it's a free action, right? And then your generalization is not asking for any G space, because that would probably be not true. But if you take any free compact G space.
Exactly. Mm-hmm.
Then
about usual Borsuk-Ulam, there were some generalizations to effective actions, but I think we are not interested in that. Okay.
Not in the stock, but I'll be interested
Okay.
in them maybe afterwards, because I didn't know that. Then there is no G map, right? So now it's everything, it should be the same as here. Now X join G to X. Okay, and for now, this is still open. There's no counterexample. So in full generality, this is open. And the question is, what do we know about the conjecture at the moment? Is that if you know, so if, let me abbreviate, if BDH is true for a subgroup, then it is true for the group. So if you
say
have
that
any,
this is an anti-hereditary conjecture.
yeah, so that's the word we are using when we talk about this property. It's opposite to being hereditary in some sense, right? So you're taking, if you prove it for any subgroup, then you know that's true for the group, and we know that the conjecture is true for finite groups. But this means that if you have any group with torsion, then it will be true for that group, because it has a finite subgroup, right? So this means it is true for torsion groups. Now, this result is, and this somehow, so one of the, I didn't say that because I somehow forgot, but this talk was supposed to be my preliminary PhD exam. So, and my whole committee was supposed to be present and judge my presentation and research and so on. And one of those, one of the people from the committee, Professor Torunczyk, asked me a question that led me to seeing that the PDH conjecture for finite groups can be deduced from a very old result. And I don't know how to pronounce those names, but I think I've got the writing right, and it's 81. It's not easy to deduce it, but you can do it, and it's not that hard also. But the problem they proved and they were looking at was formulated in a much different way. So people didn't know it and reproved it. So Wołowikow reproved it in 2005, and then Ben Passer, but he was interested in C-star algebra. So and he also somehow didn't know about the proof of Volvikov, and Ben gave 3 or more proofs of this result in the topological setting, because he was also doing C-star algebras, but he needed this result for finite groups. Okay, so that's what we know. If you have a torsion-free group, then we don't know anything. Then we know something, and this is what I'll be talking about. But before we started working on it with Ludwig and Alex, this is the state of the art. So only for finite groups and for torsion groups, which is, well, this is a big class. For example, all compact Lie groups. So that's the conjecture, and that's what we know about it. It's enough to prove it for the group of p-adic integers, but I have no space to, maybe here. No, let me start a new page. So if you're interested in proving the conjecture, then it is enough to prove it for ZP. And by this, I mean p-adic integers.
And topologically, ZP is just a Cantor set?
It has the topology of the Cantor set, so it's definitely not a Lie group, right? And it's there are many things that if you use the p-adic integers, you can provide many Cantor examples because of that topology, which is the topology of the Cantor set. Okay, but now let me go quickly through the notion of the G index, and after that I'll present the result, the state-of-the-art result, and I'll try to prove it or outline the proof. So the G index this is something that I will need. It has nothing to do with index theory, so sorry, Paul.
Oh, yeah. Okay.
So it's if you have a G, G is a group and you take a G space X, then this index is a number which is defined as follows. It's the minimal natural number n such that there exists a G map from X to n-fold join of G with itself. And it will be a definition, but you can see that it has to, for this talk it will be just the definition of local triviality, but if you know what principal bundles are, you will see from the definition that it coincides with that. If X is a compact G space, so by this I mean that both X and G are compact, and of course Hausdorff, because that's my assumption. Then we say,
So Mariusz, perhaps you should add that this index can be infinity, no? In case.
it can be infinity, yes.
Okay.
Yes, thank you. So
if there is no n.
If there's no n, then we say that index is infinity. Yep. But thanks for that. So then we say that X is locally trivial if this number is finite. And this just means, and you can prove that this is equivalent to this bundle being a principal, local trivial principal bundle. Okay. So this is the definition I need, because in the title I have Borsuk-Ulam theorem for locally compact, for locally trivial compact G spaces. So this is what I mean by this. So this is the locally trivial. And a few words is that if X is a free G space, is a locally trivial G space, this implies that X is a free G space, which we saw in the formulation of the Borsuk-Ulam type conjecture. And so if I have a locally trivial G space, it's a free G space. If you try to prove it the other way around, well, for some groups it's true. For example, if G is a compact Lie group, and this is a theorem by Gleason, or more generally by Mostov, then free implies LT also. In this sense, so locally trivial, I'm abbreviating by this LT. So if we look at the conjecture for, let's say, finite for compact Lie groups, it doesn't matter if we talk about free G spaces or locally trivial G spaces, right? So if we go back to the conjecture, and here we write down a compact Lie group, instead of free, you can write down a locally trivial compact G space, and the statement will be the same. So this will be equivalent. And the theorem that I'll be talking about, and I'll try to present a proof, is the following. So this is the theorem I'll try to prove for you. It's I know somehow. Hirvasitu, so Alex, Ludwig, and myself. It's just the proof of the conjecture of Paul, Ludwig, and Piotr in the case when X is a locally trivial G space. So let G be a non-trivial group, and X a locally trivial compact. Oh, I didn't write down compact here. So of course, non-trivial compact group, locally trivial compact G space. Then there's no G map. And so I'll try to outline the proof, but before that, let me say a few words. This is as far as we can go now with the conjecture. So if you take something which is not a locally trivial G space with G being a torsion-free group, then we don't know. But so in the proofs so far of the conjecture, we had some restrictions on G. So we were saying finite groups, torsion groups, or whatever. But X was arbitrary. But now we have a restriction on X. So X has to be a locally trivial compact G space. But G can be arbitrary. So arbitrary in the sense that any non-trivial compact group. All right. So this is the difference, and you can also prove that this is a generalization of the result for torsion groups. It's maybe not immediate, but this is generalizing the proof of Vovikov, of Ben-Passer, and so on. So this is so.
That's simply because the conjecture is anti-hereditary, as you mentioned, and it is every free finite group action on a compact Hausdorff space is definitely locally trivial. And
yes, but there's also a question. So if you have a torsion group, then you don't know if for sure that or maybe you know, I don't know, but if you have a torsion group and it acts freely on X, we cannot say immediately that it's locally trivial, but you can go through this torsion subgroup, this finite subgroup.
Exactly.
If you know that the subgroup acts locally trivial, right, then
and the subgroup, you know, restriction of a free action must be a free action, right? There is no way around.
Yes, that's true.
And then you have a free action of a finite group, that's the torsion subgroup, and then you know it's locally trivial because it's a very special case of a Gleason theorem, which you can very quickly prove. I remember we did it with Paul in his office. So.
Yeah. So that's what I wanted to say before I'm going to the proof. But also let me mention that there was some fake news that the conjecture is true in full generality. So there were claims that this conjecture is true in full generality, and Robert Edwards found a mistake in the proof of Ben and Alex, so Ben-Passer and Alex Ivasitou, who are claiming that this is true. There was a mistake, and you cannot fix it with using the same method of the proof. So the conjecture is still open, and Robert Edwards, who showed us the mistake, proved with Mladen-Bestvina the following result. So if G is a non-trivial zero-dimensional compact group, then there is no G-map of the form. I'm taking n+1 joins of G of itself to n-fold join. Right? And this is also a result that was Edwards posed this as a conjecture in some workshop on topology in '87. So that's when he conjectured it. I don't know when they proved it, but it's still unpublished. But they shared with us the insight of their proof, and it turns out that our theorem is equivalent. So let me is equivalent to the generalized we had Borsuk-Ulam, which was but. Now we have Bestvina-Edwards, which is bet.
You bet.
Yep. So the theorem is as follows. I have now the zero dimensionality can be dropped. So just non-trivial compact group. And there's no G map of this form. Okay. Let me prove this equivalence. So there will be some reasoning in my talk, because I was only just presenting some results. So proof of the equivalence. So first, if I want to prove that CDT is implying BET, I hope that there's not too much of those abbreviations, but it's saving a lot of time when I'm writing this on the blackboard. So to prove this, I'm assuming that I know that there's no
Perhaps you should put cross on the existence sign.
Oh, thank you very much. Thank you very much. So I'm assuming that there is no G map like this if the G index on X is fine. Right? So it's enough to just observe that surely for G and from N, this is less or equal to N, right? From the definition. So that's just one way you have it for free. The other way is maybe a bit more demanding. That now I'm assuming that, so I'm assuming that there is no map like that, right? Like in this theorem, so I'm assuming that I have no map like this. But suppose that there is a map of this sort for a locally trivial space X. Right? So first I have X. This is a locally trivial space, so I have some N, and there exists some N that I have this map because I'm assuming that. And now, if a map like this exists, then I can iterate the join until I have X join G join N plus 1. And I can embed equivariantly the N plus 1 fold join here, right? As this factor at the endpoint of the interval, I have this space. This one is shrink to a point, and this is equivariantly because the action was diagonal here, right? All those maps are G equivariant. So we have a contradiction with generalized Bestvina-Edwards theorem. Right, so the reasoning was going as follows. Suppose that a map like this exists, and then we show the contradiction. Okay, so are there any questions or comments?
The logic is pretty straightforward. You just you negate both theorems. So not true that CDT implies not true that BT, and not true that CDT implies that means that there is such a map X join G into X, and then show but then there is a map from N plus first power of G into Nth power of G. So that's completely natural reasoning.
Yep. So, but it still was no one noticed that for us. So yeah. I remember that's also in Trieste. I came up with this reasoning, and you all approved it. So I hope it's still.
No, yeah, we
still
maintain our approval, right?
Yeah. Okay, so this theorem is the one that I want to prove, right? Well, either of them will be okay because it just.
But this is just one-way implication. How about the other way around?
Oh, the other way around was first.
Oh, sorry, I missed. Okay, sorry.
Yep.
Yeah. Okay, yeah. Sorry. Of course. I'm sorry.
So okay, now the proof of the actual theorem.
Good morning, Eric. Well, how you feeling? What?
Paulus has guessed.
Yeah.
Well, we can hear everything.
Oh, okay. Well, I have to go. I'm very sorry. I have to, wait, are you ready to rock and roll? I am. Okay, I'm gonna go to my, okay. All right, just give me a minute here. Okay. Okay, great.
Okay,
All right, this
then
is
I
all
continue.
interesting. You have
Okay,
to get
Paul,
the
thank
Yeah,
you.
thank you, Paul.
Oh, it's a great pleasure. Okay, for a week. Okay, goodbye for a week.
Yeah, for 2 weeks actually. Yeah,
Oh, for 2 weeks. Okay.
yeah.
Okay.
Bye.
Okay. Bye
Ciao,
for
Paul.
now.
Ciao, ciao.
Okay. Bye for now.
Okay, so I guess I can continue. Now there are two main points of the proof. First is some structural result. For torsion-free groups. Now, I told you that the full conjecture for any free space is true for torsion groups. So of course, this full conjecture implies this theorem, right? So the theorem that I'm proving is true for torsion groups, right? Because locally trivial is free in particular. So that's that. So it remains to prove it for torsion-free groups. That's what I want to say. So maybe I'll write it down first. So okay, so that's the first observation. And what we'll need is a structural result for compact torsion-free groups. And this will be the first step. And the second step is constructing a locally trivial G space, compact G space, which is non-trivial. Oh, here I am. Okay. Which is non-trivial over non-trivial loops. And I'll tell you what I mean by a non-trivial loop in a second. By a non-trivial loop, a loop alpha, where X is some path-connected space, is non-trivial if it is not null homotopic. So it cannot be homotope to a constant map. So this map, this continuous map alpha, cannot be homotope to a constant map. And you will see in the proof how we use all those results, because for maybe now it's not obvious how this result will be used, but you'll see. I still have like 40 minutes. Is that true?
Yeah, I have exactly 40 minutes, yes.
Okay. Great. So let me start with 1. And the result that I have here. So first, if G is any topological group, let GA denote the normal subgroup of elements that are path connected to the identity. There will be some old school algebraic topology going on in the proof. So words like path connected will maybe appear more than one time. It's maybe not immediate that it's a normal subgroup, but if you think about it for 5 seconds, then surely you'll see that this is true, that this is a normal subgroup. And then I'll define pi0 of G to be this group. And here I'll disregard the topology. Just treat it as a group. So I'm looking at this thing just as a group. The topology might be not so nice, but this will not be important for the proof. So we just view it as an abstract group.
May I ask you a question?
Sure.
Shouldn't be G at least locally path connected? Because you are killing the path connected component of the identity. And this is pi0. So the left-hand side classifies the path connected components.
Yeah, so I might have probably I said what locally. So could you repeat your argument that, so you said it should be locally path connected? Is that the assumption?
Well, pi0 classifies path connected components, as you see from the right-hand side. But this could also mean connected components of G. So if the group is not locally path connected, then this could be different.
Well,
what's your definition?
I think if pi0, that's my definition of pi0. That's the definition.
So path connected components. Good.
Yes, because if your group, so that's a good question. If your group is totally disconnected, then this is 0. This is just the
okay. If it's your definition, it's okay.
Yeah. Okay. But it's a good question, because you can immediately see that if
because the same symbol sometimes is used for connected components.
No, I'm not claiming that this is some sort of equality of two differently defined things. This is my definition. Yeah. So if G is totally disconnected, then pi 0 G is just E. It's just G. Well, what did I say? It's G.
Mm-hmm.
Okay, so and then the result that we want to prove, which we need, is if I have G is a non-trivial torsion-free group. Of course, compact and all the time. There are many assumptions here. Compact group. Then and for any positive integer, so yeah, for any positive integer, and there is an injective map integers power of n. I'll call it phi maybe. Map phi. The integers to the power of n into G, which remains injective when composed with the projection right, so this is by a map. Well, let me change it. This should be, this is a group morphism. So let me write down a group monomorphism. Something more than just an injective map. Okay, so this is the result that we need, and I'll try to prove it, and it will use a lot of structure of compact groups. All right, and it, as you can immediately see, this will divide into two cases, because if G is totally disconnected, then we have this equality, and the part which remains injective when composed with is empty, right? So, okay. So the case one, G is totally disconnected. Right, so we know that pi 0 is G. And we have a torsion free group. So G is torsion free. This implies that, and this is a well-known result, and I unfortunately don't have time to prove it. There are also many proofs, and even Ben and Alex gave a proof using Pontryagin duality, that then the p-adic integers embed as a subgroup. So ZP is a subgroup. So it's enough to show that I can have a group monomorphism like this. Okay. So it suffices to show this. And for that, you have to look at the quotient field. So the quotient field. P-adic numbers. This is a,
or it is called a fraction field.
fraction field. Okay, well, that might be. We wrote quotient field in our paper and it got accepted. So it's probably depends. The terminology depends, but I like fraction also better. So you have the fraction field is a field of continuum cardinality and characteristic 0. So it is a vector space over Q of dimension, well, and I don't know how to, well, maybe, okay. Yeah, that's LF0. So it's a vector space of infinite dimension. That's the only thing that matters, actually. When you take some n elements, so just take V1 up to Vn, some linearly independent over Q in QP, right? Then there exists some P. So there exists some, there exists some P. There exists some K. There exists some K such that P to the K V1 up to P to the K Vn, these guys are all in ZP. And they are linearly independent. So this proves that you have this embedding. Okay, so that's case when G is totally disconnected. You only use some. You only need to prove this, and this is a well-known fact actually. So if you ask algebraists about that, they will know immediately how to go about this proof. But I wanted to present it anyway. Okay, so that's one. For two, and this will end also this will be probably the end of the proof if you want just zero-dimensional, because zero-dimensional group will be totally disconnected. So if you want to prove the original Westvina-Edwards theorem about zero-dimensional groups, this will be the place to stop. And what we have to do, is just to make sure that the case 2, when the group is not totally disconnected, still holds, and that's far from being obvious. So G is not totally disconnected. So here, if I have the connected components of the identity, then this is a non-trivial connected torsion-free compact group. So we can just restrict attention to the connected component. And so if we, maybe I'll write it down like this. So
Mariusz, just that you're aware, so Pennsylvania left, but Texas just joined.
Okay, that's great. So I thought you were talking about the elections.
No.
No.
I'm talking about our friend in the golfer, John Chow.
Okay, hi, Jincha.
Hello. It looks like I'm horribly late, it seems. I got the time
Yeah.
wrong.
Yeah, because we're talking about not totally disconnected things already. So
Sorry for the interruption then.
sure. Yeah. So restricting our attention to the connected component of the identity. We will assume that G is connected. Right? Because if not, then you take this connected component of the identity. And now we have, by Z0 of G, I'll denote the connected component of the center. Of the center of G. And now we have, I said this far from being obvious, this part 2. We have a theorem, and let me just write it down. This is of course part of the proof, but it's just a separate argument. It's called Levy-Malchev theorem, or maybe it's a generalization of that theorem. I don't know. But the important thing is that if G is a connected compact group, then there exists a family indexed by some index set J of simply connected compact Lie groups. And a continuous group homomorphism as follows. You take the connected component of the center, you take the product with this infinite product, and you put this into G, and this map identifies with its copy inside G. Okay, and that's a black box that I'm showing at you. I'm not going to prove it or discuss a lot about it. What matters for me is that you have this map, and this theorem will help me to prove that the group G that I'm working here is abelian. Okay, so that's why I need this theorem. I need to show that somehow this part will map to 0, and only this center part will survive in this map. And how this goes is just that I have this theorem now, and I know that G, that I write only continuous and continuous group isomorphism. I'm sorry. So G is just looks like this. That's why I talked about some structural results on compact connected groups. Because it just tells you how any connected compact group looks like topologically. So now we know that G is this thingy. And then if these guys are Lie groups, right? And we know that torsion elements are dense in Lie groups. So this in fact means, because G is assumed torsion free, then, oops, well, it has to be abelian, right? Because this part has a dense, the torsion elements here in those Lie groups would be a dense subspace in each of any one of them. And only the center will survive if we assume that G is torsion free. So G is abelian. And now there's some going through some other known results. You can prove, so I'll not state those results, but you can prove from that if I have any, so the result is that I have G abelian torsion free compact group. It has to be of the form, so G has to be of the form some vector space over Q hat, so the Pontryagin dual of Q, where P is just some set. Right, and here I'm using a lot of results that I cannot prove to you here, so I'm sorry for that, but that's how the proof goes. I just wanted to show you the methods used in the proof, that it was not that obvious to go from zero-dimensional to and totally disconnected to any torsion-free group. Okay. So this we know that this group has to be of this form, and now since G is abelian, so we have this map. So if I have a map Gn, if I would have an embedding like this, by projectivity, it would lift. So this lifts to Zn is projective for abelian groups, and G is abelian. Now this lifts to an injection like that. The other way around, I'm sorry. Right, because it has to, if I have this projection, this embedding, then it will lift to G. And this is by projectivity of Zn in the category of abelian groups. So now we have, it just suffices to argue that I have a copy of Zn here, right? And now, so this will mean also that if I have Q hat, right? G is just of this form at the moment, of the form Q hat to some power P. I have this embedding this will give me an embedding of by 0 groups just via one of the factor embeddings here, right? Just for some Q. This implies that we only need to show that Zn embeds here in this for this guy. And I know it's getting a bit complicated, but it suffices to prove that. Suffices to prove this thing. And this we know, and we know that this group, there's a paper called "This Group is Isomorphic to R." So that's the title. This is by Viegel. So we're back to the first reasoning, because R is a field of characteristic 0, continuum cardinality, so you can embed Zn here. And so that's the end. It's what was a bit complicated, maybe I presented it much complicated than it looks like, but yeah, just fitting into one slide, that would be it. And that's a very important result. So, but let me just quickly go to the second part, because now I'm getting out of time. So what I want to prove, because we maybe forgot. So the theorem that I want to prove is that for G, which is a non-trivial compact group, I want to prove that there is no map like this. And for that, I want to construct a space X, as I told you, which is non-trivial over non-trivial loops. I only tell you that the construction of this space. So take Rn with standard sigma Zn action. Okay. So the standard action means just that if I look at the orbit space, I get the n torus. Now we know that there's a map like this. So that was this whole theorem was talking about this map, right? So we know that we have an action. So via this map, we have an action of Zn on G. So we have an action on Rn, we have an action on G, and we construct space X to be the associated bundle . And both actions are on the left. And we'll consider the right action of G on itself. So now the first observation is that if I look at the action on X, which is just the right action on this component, then X is a principal, so G is a principal G bundle.
Over the torus, right?
Over the torus, yeah, thank you. So because this guy would be Tn. Right?
You should write right action with G arrow from the right.
Oh yeah, that's true.
Sorry for
It's
that. No,
because
it's okay.
if you have the fact is that we want the actions of if I look at the action of Zn here and the action of G here, we want these actions to commute, and because the group might be non-abelian, right? So yeah, so that's that. Yeah, and this it's not so hard to prove. It's just the fact that this action of this is just the action on elements. So you just write down all the axioms and you try them out. What is nice is that you already have a nice principal action of Zn on this. So it shouldn't be too hard to show this. And also this is just by the associated bundle construction, you can see it. So now the part is that I told you that we want to prove that this is non-trivial over non-trivial loops. And what I mean by that is that if I have a loop in Tn, and I have this bundle, if I pull back, then this bundle is non-trivial. Right? So if alpha is a non-trivial loop, so this is the claim. Then x is x over, well, no, that's alpha star x. The pullback bundle is non-trivial. It's non-trivial. As a principal G bundle. Yes, that's what we want to prove. And then just some really standard algebraic topology reasonings. So just lifting those paths. If I have a path alpha, I can look at this map starting from 0, 1, then map Q will be a map which identifies the points. And I'll define the map beta like that. And beta can lift because we're talking about universal covering of Tn by Rn. So beta will lift some map 0, 1 to Rn. And then you define beta tilde from 0, 1 to x just by taking T to beta T and taking the neutral element. Right? And at this point, what is really important is that you have, well, this you have to check, but this for this map, this beta tilde, if you take beta of 1, but this is just a simple calculation. If you know all the definitions and know how to lift a path in here, you can prove this thing. Remember how the action is defined.
Sorry, Marsh, this map from the unit interval to S1, this is what, just gluing the endpoints? That's what you mean?
Yes, yes, yes. So this is gluing the endpoints. Yep. Okay. And so this is what we have, and we can. So if we glue the endpoints, you can prove. If you write down all the maps, unfortunately, I don't have time to show
You
the
recall what is A?
Alpha. Yeah, alpha. I'm looking at alpha. I hope I didn't mess. I think this is okay. But beta also will factor. So beta has to factor because we can write down a commutative diagram. So we have.
Sorry, and what is phi?
So phi was defined from the very beginning. It's this map. It's this embedding.
Okay, from Zn to G.
So
okay.
you have an element in G, and you act from the right. Right. This is what you get. You get this formula, And then you know that beta has to factor. And how do you see that is beta factors element which I'll call Q tilde, which goes from 0, 1 to alpha star X.
And when you write the class of a loop, you mean what? Homotopy class?
Yeah, a homotopy class. So because you start with a non-trivial loop, so you know that this class, sorry for that. Yes, that you have a class in pi1 of Tn, which is exactly Zn. Yeah, that's a very good question.
Okay.
Which is Zn, right? So
okay,
and
so
you,
now I
you
can
know that
put
this
these pieces together. Yes.
Yeah, thank you. And this is non-trivial by the assumption of non-triviality of the loop, so it cannot be homotopy to a point. So you have this, and you can write down this formula. And now, if you go, and this has to factor because this is a pullback, right? So it has to factor to some map from 0, 1 here. Maybe if I would like, I had this map to Tn. I have a map here to Rn, and now this is a pullback of Rn and G. And now I have and this is how I defined this bundle, right? So I have all that. So this has to factor, and this Q bar still will satisfy the same formula. Maybe the things are different right now, but just believe me, if you write down all this is nothing fancy. This is just plugging in the definitions. And it ends with the following. So I know that this is if this is a trivial bundle, so now suppose this is a trivial bundle, I will have some map gamma, which is just, which just goes from 0, 1 to by Q bar to alpha star X and to G by triviality. And I'll have a map gamma for which I'll know that this is satisfied. And this is some non-trivial element. And this also lies in the path connected component of 1, because we know that phi, when you compose it with the quotient, right? When you quotient out by this normal subgroup of elements connected to path connected to the identity, this still is not non-zero. So this contradicts the assumption of homomorphism phi, because now it's suddenly you can connect it by a path to the identity. Is that no? This contradiction is just the assumption that phi lies in the connected component of 1. This is what I wanted to say. And this is how we know that the bundle is non-trivial over non-trivial loops. Because if it would be trivial, then you can have this reasoning, all this algebraic topology leads you to this contradiction. And the proof ends, I'm already over time probably. Yep.
I have 1 minute.
Let me just say how the proof ends. So it goes like this. Suppose that the index of G is equal n minus 1. We know that it surely is less or equal to n, but suppose that this is n minus 1. So I have, and we know that x is locally trivial. So take the n, so we know that x is locally trivial, so take n to be this n for which I have the map, right? So that's my n. And suppose that the index of this guy is less. So I have this map, which I'm trying to prove that it doesn't exist. Okay. What do I do now? Is that I can now take, we know that I have n-1 open sets that trivialize this bundle. I can pull them back here to the torus. And I suddenly have n-1 open sets trivializing x over Tn. And now the assumption that this bundle is non-trivial over non-trivial loops shows you that, so this is a crucial, so the assumption on X shows you that if those open sets, I will call them UI, those maps cannot be null homotopic. Because if I could homotop this, let me just say this in words. Because if I have it's non-trivial and non-trivial loops, so UI cannot contain a non-trivial loop, right? Oh, I said cannot. There are no homotopic. Sorry, I'm just trying to do it too quick. So the existence of non-trivial loops in the connected components of UI would mean that the map at the level of pi1 groups are trivial. And this would imply that this factors through the contractible universal cover of Tn. Oh, I'm not sure. So this will factor to the universal cover of Tn. So they cannot be, so they are null homotopic in fact. And this contradicts, so the whole point of this proof and of showing that this bundle is non-trivial loops was to say this. And if you know that, then this contradicts a famous and well-known result on Lusternik-Schneelmann category, that the number of such, the cardinality of such a covering, so cardinality of such a cover is, there cannot be less than n. Then n for Tn. And this is under the name of Lusternik-Schneelmann category.
So you get the desired contradiction and the index is n as claimed.
Yes, so this is the contradiction, so the index has to be n, so it cannot be less. Yeah, so sorry for going over time. But yeah, so that's what I want to say. Let me just finish up with one sentence. The whole proof of Edwards and Pestvina and their idea is on this slide. So this is something that we borrowed from them, but to prove it for not only for the zero-dimensional group, you had to work with this theorem, this kind of structural result, and also to prove that this bundle is non-trivial over non-trivial loops. So this slide, this was given to us by the referee actually. So we had a different proof of that for because it would be much easier for just a zero-dimensional group or something which is totally disconnected. But with this reasoning, you can prove it for any G. And this is actually a nice lemma given to us by the anonymous referee of our paper, which is really basic and based on algebraic topology, which you can learn as an undergraduate student. So I find it really cool. And all that was needed to just go to this contradiction, because we need some, anyway, to prove any Borsuk-Ulam type result, we need some invariant that we know exactly the value of which we know exactly. Like for this cardinality of such a cover that I described. So a cover of Tn by sets such that these maps are null homotopic. This is called the Lustening-Schneemann category of a space. So, and we know that for Tn, this is exactly n. It cannot be less. And that's the contradiction. So yeah, so sorry for going over time. And that's the state of the art of the Borsuk-Ulam type conjecture of Paul, Piotr, and Ludwig. Thank you very much for your attention.
Thank you, Mariusz.
Okay, thank you.
Before I will ask you guys to ask Mariusz questions, first, let me have a quick go at Mariusz. So first, is it the same reasoning as you had in your thesis, or this referee stuff is something new?
This referee stuff is new.
Okay, so it was not in your thesis. So when you are explaining it to me as part of a thesis, it was a different reasoning.
That's true. Yeah, it was
okay.
Much more complicated.
Yeah. Okay, good. And now I really have to make a self-correction first because it's very embarrassing. When Paul asked a question about this dimension, I gave a stupid answer. It's exactly the other way around. You can diminish the dimension of the Euclidean space of the right-hand side in the Borsuk-Ulam theorem, right? But not increase it, right? So you can have it that there is a map that for any map from Sn to Rm, there is such and such antipodal property, and you can take this m to be less or equal to n, but not more. Obviously, when the dimension of the Euclidean space is even one higher than the dimension of the sphere, just have the embedding, which doesn't identify any points. So it's obviously wrong. Sure. But if you make it smaller, then you can quickly, by having some simple reasoning, and quickly convince yourself that indeed, if any map has such property, any map from Sn to Rn has this property of identifying antipodal points, that any map from Sn to Rm with m smaller than n also has it. That's an immediate conclusion. And it's also natural because the smaller the dimension of the Euclidean space is, the easier it is to identify points. At the end of the day, you can have just one point and then everything is identified and the property is trivial. Right, so sorry, I just had to self-correct myself because it's very embarrassing to give a wrong answer.
Sure. But I think that Paul got it right?
Yeah. Okay, now that it's done, I have one more comment, which I think we must make, namely that the conjecture that Paul and Ludwig and I have, it's actually for quantum groups and C-star algebras. This is the commutative version. And I find it very fascinating that even in this purely classical commutative setting, we can still do something new. And you didn't mention it in your talk, but I think it's very important to stress it, that a reason why our conjecture is so difficult to prove even in the classical setting is because it implies the famous weak version of a Hilbert-Smith conjecture, which is an outstanding open problem. So that's there will be no shortcut. There will be no easy proof. Okay, so that's another thing I wanted to say. And what else? Maybe it's worth mentioning that here what we used is that the state of the art is summarizing this property of local triviality. So if our G spaces are locally trivial, our conjecture holds, and it particularly implies the torsion claim. But this is no longer the case when you go quantum. When you go quantum, we have two separate theorems. One which claims it for quantum groups with classical torsion, and one which claims it for quantum groups with classical subgroups, such that everything is locally, such that after the reduction to the restriction to the classical subgroup, we have something locally trivial. So there is no longer an implication. I think we found explicit examples of free actions of finite groups on C-star algebras that were not locally trivial. So there are some very nice quantum issues appearing, but that's yet another talk. And let's open a quick discussion. So if there are any urgent questions, please fire at will.
May I ask you the question?
Sure, go ahead.
Okay, in your argument about using this illustrative cinema category, you have this condition about null homotopicity of these embeddings of UI.
Yes.
So a big part of theory of free actions, principle of bundles, depends on homotopy. Your joins of copies of G is an approximation of a universal free G space. So I wonder what part of your arguments depends on the specific realization of this approximation of EG, and which parts hold for any approximation of EG by sufficiently high connected models of this EG.
So my guess would be, because I never checked it, but my guess is that it will work for any approximation. But I never checked it. But it seems that, first of all, if you look for the at the theorems of Edwards-Bestwina, and also there's a theorem of Matuszek in his book, which depends on this result that I mentioned from 81, where he uses any for finite group. So suppose you have a finite group and he uses any approximation of the universal G space. So just E and G, right? And then everything works for finite groups, but I never checked it. I was always satisfied with this one realization of E and G as the join. Because that's, so my answer is as follows. I was only interested in this one because of noncommutative topology, where we don't have any other approximation of the universal kind of quantum Milnor G space, which is a part of a new project I'm doing now. So it's a bit of commercial, or you can see it on ResearchGate. There's a new project appearing. Please read and subscribe.
Okay, thank you.
Anybody else? Well, if not, we are very grateful to Mariusz for his very nice talk, Blackboard talk. And let me make two quick announcements. So next week we have a national holiday, the end of the First World War. So there will be no seminar. We will resume in 2 weeks. And another thing is, I apologize for the confusions with GMT+2. You see, GMT simply does not change itself when you change from winter to summertime. So probably when I Googled up how should I claim Warsaw time, I found that it's GMT+2, but now it's GMT+1, and some people were confused. So my apologies. I always mean the local Warsaw time for the seminar. And maybe this is why Jian Chao got late, because of this confusing equality that Warsaw time is GMT+1, because this equality changes in time. So that's all I wanted to say. Okay, so I'll stop recording. Thank you very much.